Example of, okay, our next example of linear functions is an electrical circuits example. It tells us that an electrical circuit with direct current is comprised of a voltage source, a resistor, and an additional voltage drop. The relationship between the voltage measured in volts required from the voltage source and the current measured in amps flowing through the circuit is described by a linear function Vs of I equals R times I plus Vd, where Vs is the voltage source when the current is flowing through the circuit is I, R denotes the resistance measured in ohms of the resistor, Vd denotes the additional voltage drop, and then it tells us that at a current of 100 milliamps, the voltage source was 10 volts, and then at a current of 1100 milliamps, the voltage source required is 20 volts. And then asks us a series of questions that we'll answer one by one. So, as always, the first step is to set up, I've already set this up on my engineering paper. Drew a quick diagram of the circuit. We've got a voltage source, we've got our voltage drop, we've got a resistor, we've got the current flowing through it. We've named all of our variables and included units. We included our equation here that they gave us and the points that they gave us, current, the voltage source for those given currents. And then we're going to work through these parts piece by piece. So part A, as we've come to expect on these example problems, asks for the independent, the dependent, which one is the slope, and which one is the intercept. So, solution to part A, the independent variable is the one that is a function of, so that must be I, which is our current measured in amps. The dependent is the one that it is a function of, so if our function is Vs of I, then Vs must be our dependent variable. And so our voltage source is measured in volts. Again, one of the nice confusing things about circuits, you get a lot with voltages, and the units are, which you use V for the variable, and the units are in V volts. Can be very confusing, but we'll keep up with it. And then it wants to know which one is the slope and which one is the intercept. Again, we can think back to recognizing that our equation is in point-slope form. So if we, again, think back, and at some point your brain will just recognize this without having to use the same mnemonic of putting it back into the old terms of y equals mx plus b. But when we do that, we remember, because this is the independent was our I, our dependent was our voltage source. The slope is the one that's multiplied here, so R is our slope, and Vd would be our intercept. So there we have our resistance in ohms and our voltage drop in volts. Side note, if we look at this term, which is R times I, resistance times current, that must be in volts. It must be a voltage because we're adding up voltages here. So R times I is a voltage, and that comes from Ohm's law. That's something you learn very early in working with circuits. And you can, of course, manipulate this around and get R equals V divided by I. You may see it written as that. Or you may see it as I is equal to V divided by R. All those are just different forms of Ohm's law. The other thing that's interesting about this are the units. And I'll go ahead and go back and label this in terms of VR, the voltage of the resistor, just to kind of be clear about which voltage I'm talking about here. But if I'm talking about it in terms of units, and I use these little brackets to indicate it has units of resistance is in ohms, current is in amps, voltage is in volts. So ohms times amps actually gives me volts. You can do a little bit of breakdown in determining how that comes about, but that's just one that's always true that we can use in circuits going forward. So moving on to part B, we find that we're trying to find what the resistance and the voltage drop are. We want the numerical values of these now. So resistance, we know, is the slope. So it's the change in voltage source required for the change in current. One of the things we run into here is that these are both in milliamps, so we would want to convert those. And it's very easy to go to milliamps. We want to get them to amps. So 100 milliamps, we would move the decimal point 3 places over. That's the same as 0.100 amps. And 1100 milliamps, similarly, would be 1.100 amps. So again, for milli, to get it back to just regular, we move it 3 places to the left. You should get a smaller number of amps than you get milliamps, because oftentimes we think of it going back the other way. If we had 0.100 amps, we'd move it 3 to get 100 milliamps. So I plug in my values. I take the 20 volts minus 10 volts divided by 1.1 amp minus 0.1 amps. So I get 10 over 1, or I get 10. Because this is a mixed operation, I'm going to round to 3 significant figures, so 10.0, and the units on R should come out to be ohms, which is true because, again, if I have voltage divided by amps, I get ohms, which is what we just learned a minute ago. Okay, so the next part of B is I have to figure out what the voltage drop is. So I can rewrite the equation now that I know the resistance. I can go from, I know the voltage source is now 10, which is my resistance times I, plus my voltage drop. I'm going to go ahead and solve for the voltage drop first. So voltage drop is the voltage source minus 10 times I. Plug in values. Just to let you know, I used the first point. You could use either one. You could have done 20 minus 10 times 1.1. You should get the same answer of 9.00 volts. And again, that's a good way to check things, is to try both ways and make sure it works both sides. All right, so now if I know that, then I can rewrite the equation. I know that Vs is equal to 10.0 times my current plus 9.00. And they didn't ask me explicitly for this, but it's always a good idea once I know my equation to write it out and box it there. All right, so part C is asking for a sketch. So again, I'm gonna start over here on a new page because we ran out of room on the other one. Use my equation, and then we'll make a quick sketch. So again, assumptions I can make is that we're only worried about positive current values. So that we work in that realm. And then to make a meaningful sketch, I need to know a few pieces of information, and the fact that I know the slope and the intercept is good enough information. So for just a sketch, this is sufficient information. I've got the intercept, I've labeled my axes, I've got the slope. One key point of information on this is, again, we think about end behavior, and I've already marked this one. On this end, we assume that as the current keeps going up, we're just going to keep needing more and more voltage source. So that will keep going forever. Here at 0, nothing actually happens at 0. So we'd actually want to leave a hole here at 0, because if there's no current, there's no voltage. No voltage there either. So that would be minor adjustments we would need to make to our line there. Moving on to part D, we were asked for a current of 250 milliamps, what voltage source is required. And so another way to think of that is Vs of 250 milliamps. But again, what does that equal? And again, the first thing we should remember is that our function is given in terms of amps. So we should first convert that, and what we're really asking is what is Vs of 0.250 amps. And so if we do that, we've got our function. All we have to do is plug it in now. We have 10 times 0.250 plus 9, and we get that value. And what we get is, you almost don't even need a calculator. What we get is 11.5 volts. And again, because it's mixed operations, we would use 3 significant figures. Although if you put 11.50 of -2 upset, because clearly, based on previous data, we have the ability to measure our voltage down to the nearest hundredth. But by our rules, we go with 11.5. Part E Again, it asks what's the voltage source required for a current of 750 milliamps. So again, first thought is to change milliamps into amps. So we're wanting Vs of 0.750. We plug in the value, 10 times 0.750 plus 9, and we get 16.5. And the other thing we should be asking ourselves as we get these answers is, do they make sense? And since we've got a sketch there, it's real easy to think about. So if we were at 0.25 amps, we'd be up here at 11.5. That's probably good. And at 0.750 amps, we'll be up here at 16.5, which probably makes sense because we know at 1.1, our previous, we knew that 1.1 we were at 20, and we know at 0.1 we were at 10. So the fact that we're still in between those values for values that are in between here makes sense. Part F tells us that we have a voltage source of 15 volts and says, well, what would the current be? So we can start with there, use our equation, and just solve for I. So we set 15 equal to 10 plus 10 times I plus 9. Subtract the 9 from both sides, I get 6 equals 10I. Divide by 10, I get that I is equal to 0.600. Again, I would want to use 3 significant figures because it's mixed operations. Also, because all the other things have been reported in milliamps, I might also report it that way. Since we're reporting milliamps, that would become 600 milliamps, and I would leave the decimal point to show that it does, in fact, have 3 significant figures. So that's how, and either one of these would be acceptable depending on how the question asks, but you got to make sure you have the right units with that number. Part G asks the same type of question, only now our voltage source is 25 volts. So again, I'll set it equal to our equation and solve. So for our current on this one, I would get that it's 1.6 amps or 1600 milliamps. So again, simple enough to solve that one. If I was doing this over and over, I've already done it twice, had to solve for I given the V of S. One thing I might want to do, as it asks in part H, is what is the inverse function? So if I know Vs, what do I have to do to get I? And we've talked about on previous examples, there's 2 different ways to do this. One is I can start with, I know the equation. I can take our particular example and solve it out. But basically what I'm doing is I'm going to set it up like this and then solve for I. Or I could do that by taking the generic equation, solve for I, and plugging in those values I know for the resistor and for the voltage drop. So either way I want to solve that, I would subtract this constant from both sides, divide by the slope. And those are both true statements, but generally, again, we're trying to look at it as a function. So what we want to do is separate that out so that it looks like a slope-intercept form. And you can see either way I work that out. Either I can just go ahead and do the division here. And again, generally when we do these things, we want decimals for these coefficients. Sometimes you might see them as at least a simplified fraction. So 1/10 might have been okay here, but or 9/10 here. But if you have something like 9/3, you should definitely simplify that down to being 3, or as I said, you should reduce it as much as possible if you do leave fractions. But generally, for engineering purposes, we like decimals better. And so you can see there, again, either way you go about it, you can either do the constants or you can do them as variables first and then put in the values. Since our resistance is 10, 1 divided by 10, we get 0.1, or we get minus 9 divided by 10 is 0.9. And they didn't ask us to, but I went ahead and did it here in blue. If they asked us to sketch current as a function of voltage source, we know that, again, we would not worry about things in negative terms, so we would ignore everything past this. So the first time we would see anything would be happening when we get to 9 volts. We still have mathematically no current. So we would have a hole, but once we get past 9 volts, then current would start to flow. And we assume for whatever voltage source we continue adding beyond that, it would keep going. And we have a slope of 0.1.